Okay, Godwin got question. Please ask. You can talk. How do you know a microphone is microprocessor is what is your OTP here? Or that one here is because, okay, if your microprocessor is one-time programming, it means that, okay, they are not programmable. Okay, so only the factory, okay, making use of special instruments to download the program, and then that's it. Those are not can do many times one. Usually they have a name called programmable. Okay, programmable. So the VHDL, the Cyclone 2 is programmable. Of course, okay, even though programmable doesn't mean that, okay, it is no limit. So they can program, say, like 1,000 times this type of limit. And the one that we use for our lab here, every time or every semester, okay, maybe the students will try, one student will try 5 times, things like that. So it still can last for quite a number of years lah. Huh? Looking at the part number, I don't think so. Okay, so you look at the part number, of course, okay, you can go to this Google, Google to type in the part number, then Google will be able to tell you. Like just now, okay, I went to Google to check this wait, this DE2 pin assignment. Okay, I didn't get a good one. I just want to see that, okay, is it possible to check? Okay, so I go to Google. You type in the pin number, Google will be able to tell you. Okay, they have all these informations. So these are the pin assignment that information got from Google. Okay, from the data sheet of this DE2. All right, so there are many switches. Okay, switch number are all in. There are 18 of them. So which one you want to use, you just assign the pin number. Okay, so if your one is D2 FPGA, the technology that they use is FPGA, so you choose this one. If yours is D270, all right, is an enhanced version, then you choose according to these pins here. All right, there are actually a lot of them. Okay, a lot of them. Okay, remember there are also these IO port whereby you can do expansion. If you want to make use of it, you have to assign it. So in my lab manual, I only pick those we are using. So if you want to know all, please go to Google to find out. Okay, so everything. So this is a hex. Okay. So hex, they are all in 4, 6, if I'm not mistaken, 8 of them. So everyone they will assign and let you know. So don't forget, just know where to get enough already. Okay. Going answer your question. By looking at the part number, nobody is going to remember the part number. So many of them go gila one later. Okay, Ming Hang, you are here already. You forgotten about the lab or what? Yun Shen, still not in, is it? Okay, so I start the lecture. So a little bit more to go to complete our topic on this VHDL. Now in this, okay, start. Hey, sorry. This is the one. This is the one. You mean that I missed out this? Okay. Now, in this VHDL for today, we are going to look at, okay, how we are going to write program for things like okay, how we are going to write the program for this type of say like a state diagram. Okay, so just choose one that is a very simple one. All right, so before we continue with the sort of writing the VHDL program here, just get a little bit of general information. Okay, so sequential circuit also can be called as a state diagram, state machines. okay, state machine. So in VHDL, if you want to write program for state machine, you at least must have two process statement. One actually is control the clocking. Okay, one controls the clocking. The other one, okay, you actually explain the state diagram. So usually we use the if then else statement, including the case statement. Right, you'll see the example afterwards. So of course, okay, you are going to define your own current state and the next state. You define on your own based on the state diagram given to you. Okay, and our transitions here depends on the conditions, the input conditions are, then we decide, okay, what will be the next state if we are now currently at this current states here. Look at the input condition, where shall we go for the next state? So here says that transitions depends on the current state, and if your this circuit here with the input, then of course, okay, it also depends on your input. In some circuits, okay, some sequential circuit, very simple one, okay, like those counter, okay, whole thing is depending on this clock signal only, then you find that this input is not available lah. All right, that's why optional. And outputs here depends on, okay, what type of machine are you referring to, or what type of sequential circuit that you are referring to. For the case of Moore model, you are going to find that output only depends on the current state. Whereas in the Mealy model, okay, Mealy model, you find that the output here depends on the current state as well as the input. Okay, so definition for this, okay, states here depends on your current states, and output depending what type of model are you talking about. Okay, so we look at the plot diagram of these two different types of model, plot diagram of it. Mm. So any question can pose here if I can see. Okay, now over here, now the first one here is a Moore model. You have your transition functions. Okay, this is my input. I is my input here. Okay, go into this transition functions. O is my output. And you look at this O output here, only depends on the generate functions, which is actually the state only. Okay, the states only. Whereas in the Mealy model, same, okay, input, output, but these are outputs here beside, okay, depends on this generated, okay, functions here. Your this input also playing the role, okay, to cause the outputs here. Of course, when we are talking about this type of state machine or sequential circuit, definitely you have a name called clock. Okay, whether it's synchronous or asynchronous. All right. Okay. So just an idea of this part here. We'll go into more details on of this type of sequential circuit design as well as a state machine design, okay, in the later chapter. Okay, now in studying more details on this finite, FSM stand for finite state machine. Okay, finite state machine structures in VHDL. So you find that, okay, normally, okay, I have an input, okay. So this is the combinational circuit. Combinational circuit means that it contains all the no gates only lah. Gates remember your AND gate, your OR gate, your NOT gate. Other than this, okay, you have your NOR gate, NAND gate. Okay, if you want further, then your XOR gate and your XNOR gate. Now, I cover all the gates already, okay? So, if you are using all these things here, it is categorized as a combinational. All right, combinational, because their output just depends on the input itself. Okay, so they no need to know what is the output, okay, previously. So you call it combinational. So your input normally go into the combinational circuit, and this combinational circuit's output will go into this type of so-called state register, which is actually sequential containing your flip-flops. Okay, flip-flops. And of course, okay, if you are using flip-flop, definitely there is a clock input be it synchronous or asynchronous. All right. So the output of these flip-flops here, of course, okay, will show you the state, where state and I are currently at. Okay. So now here, this current state may bring back to the, it is a sequence, okay? It will bring back to the this combinational circuit to be processed here again and output, okay? So in a process. Current state, okay, sometimes you may also want to know the output. So it goes into here, your this third process here. Okay, so your this current state here in this third process here, maybe will contain just a simple AND gate or maybe a simple OR gate, whereby they combine the states as well as input if you are talking about millimodal. Okay, so that's why here is putting as a dotted line. If it is millimodal, yes, okay, input will go into this part here. So if it's more model, you may have just okay these output states here containing okay, say for example output from the flip-flop 1, okay, and the output of the flip-flop 2, for example. Okay, if it's more model, okay, more model, they take the output okay only based on the states. So this is a block diagrams only. So we will learn how to design all this, okay, in the later chapter. All right. Okay. So look at the, okay, now I want to look at the example, okay, of building my Vhdl code for this simple, okay, you call it as a state diagram. Okay, this is a state diagram. Okay, these are state diagram here. We say that, okay, always very kacau. Okay, these are state diagram here. We say that, okay, we are trying to check for consecutive ones. Okay, 4. If I can get 4 ones, okay, continuously, then my output will be a 1. So in this case here, these are state diagram, make it very simple. They only tells you the input. So in other state diagram, you may find that, okay, I put it this way, 1, this is actually indicating my input. Okay, I put a slash, then this part here indicating my conditions of my output. Okay, so every one of these, okay, you have this. So 1, 2, 3, 4 already. Okay, 4 already. Okay, you are going to output a 1 here. So this one, 5 also, they are going to state at this one here, they are going to output you a 1. Okay, so the rest output 0. Now, this output 0 or output 1 here tells you whether they successfully detecting the 4 consecutive ones or not. You will see output, okay, change from 0, 0, 0, 0, 0, this 3, 0, and then the fourth one, okay, comes to a 1. That is to say that previously, okay, I detected 3 ones already. And now, when I detect the fourth one, okay, I'm going to tell you, okay, successfully detected 4 ones, one shot. And if the fifth one, okay, is still a 1, or sixth one also a 1, and subsequently all are 1, you find that the output keep on showing you a 1. Why? Because that it indicate that, okay, they take the newest 4 ones, okay, the newest 4 1, or the latest 4 1. So keep on detecting the 4 ones already. Okay, so this is the block state diagrams, okay, for this part here. And now, okay, we are going to use a VHDL to sort of model this. Okay, so as I mentioned earlier, okay, we need two process. Okay. So the first process here that we are going to look at is we are trying to describe, okay, describe this state diagram. Okay, so this entity here, because quite long, so just squeeze it in this case. So entity, name this one here as counter. Entity counter is, okay, I have an input clock. This is my I input. This I input is this one. Okay, what is the input of this one? Okay, I input. And there is a reset, okay, that is going to control or to make it, okay, start from the very beginning state, which is the EO. So this is my initial starting state. Okay. So sometimes, okay, you will see that, okay, IS, initial starting state, IS. Okay. This is the IS, initial starting state here. They are going to move when they detect something. And this movement here controlled by clock. Okay. This clock. All right. So using very simple, only just use input and I use the bit here. Just make it very simple. Then my output here either showing me a 0 or 1. So out bits. So end this counter. So my this counter here, 3 inputs, 1 output. Okay, 3 bit, 1 bit. Okay, then the architecture here is I define my own state types. Okay, so architecture automate of counter is type state type. I define, user define. Okay, is just now in the block diagram, you see the EO, E1, E2, and so on. So you can put anything as you like. All right, based on the state diagram given or you design. All right, and then, okay, after defining these states here, I must declare signal. By this signal here in sequential circuit, usually we have something called state, which is a current now. State, that is the next, after 1 clock pulse. So after this one, they will come to here, become next lah. Then the next at that time actually become current. So this current and next here all are referring to time. Okay, this is at t equals to 0, current state. This is at t equals to 1. So, do I make a mistake? Okay, now next state, this is the next state, is at t equals to 1, referring to time. So when at t equals to 2 that time, you find that, okay, t equals to 2, this one here from next state is going to change, become current state. And this is the new next state. Okay, because your clock is continuously, isn't it? So the current state and the next state keep on changing. Okay, keep on changing. Okay, then over here, if you are using short form, very general, we use CUR state. Okay, stand for current state. Lazy a bit. Okay, next state, you can, okay, use it to represent this one. CK is your clock. I mean, quite easy to recognize lah. Okay, don't use, okay, those are funny, okay, no, short form, when people ask you, cannot recall. Okay. Okay, so like I say, okay, these are process here, first process here. I'm going to describe the state diagram. So over here, I begin, and you know that, okay, this state diagrams here, okay, is going to sort of, okay, react every time when there is some changes. The changes that we are referring to here is the current state, your input, as well as the reset. Okay, you see, you never put the clock here in. Current state is the one that actually link all of them together. Okay, current state. So I begin. If my reset is a 1, then my next state is EO, output is logic 0. Indicate to me starting state. Okay, is actually EO. Because reset, okay, make you, okay, go back to the very first state, okay, which in this case here is EO. All right, and output is a 0. Okay, if my reset is not functioning, I will fall into the else statement. Okay, my reset is a 0. Go to the else statement. Then I check the conditions of my current state. There are possible that, okay, this current state could be at EO, E1, E2, or E3 subsequently. Therefore, in this case, don't just use if current state is and so on. So you find it very difficult to sort of understand and keep track of what state are they in currently. So therefore, we use the case. Else case, current state is. Okay. If your current state is at E0, then, okay, you do this. Check whether my I is it a 1. If yes, next state I go to E1. Else I go to E0. Okay. Maybe in this case here, okay, you check this part here, and let's erase this one, and I'm going to put it at the side here, easy for us to see. Okay. Why cannot pull? Sorry, okay, this part here. This PC. Well, I don't know what is the problem. Seems I cannot do it this way. Okay, now all right. So with this one here, okay, we check and see these plot diagrams. So here tells that, okay, case current state is when I'm at EO, all right, EO, when at EO, you check the input condition if it is 1, okay, if it's 1, this one, all right. The next state you are going to go will be E1, okay. Else, if your input is a 0, okay, you are going to stay at EO. So the next state you assign, okay, you are still in EO now. And under this condition, just now I told you all that, okay, I am going to output you a 0. Okay, so output 0 for this case. So very easy. Now I focus on this and I see the next state. Subsequently, what happened? Okay, my current state now, second clock pulse, I reached this E1 already. So when E1, I again check what is the input. If it's 1, next state I go to E2. If it is 0 comes in, then it go back. Okay, this one go back. You focus here, then you assign where to go for the next state. And the output in this case here, still 0. All right. Third, now I focus at this E2. 0 come back here, 1 go to E3. So I check the condition. Okay, then go to E3, else go to E2. Else in this case here means that my I is a 0 already. This else refer to this if. All right. So we usually never write again, okay, I equals to logic 0. No need. Understood. This part here indicating that my I is a 0. Then I output you a 0 at this instance. Okay. Continue with when I'm at E3. Okay. Check again. If it's 1, I go to E4, okay? Else, okay, the next state, okay, I go to the E0. So in this case here, okay, they want it to be after 4 clock pulse, only the 5th one, okay, I'll put you a 1, therefore they put a 0 there. My initial, okay, thinking of, okay, this one here, I can check the fault, straight away give you a 1. Now it depends on you, okay, the programmer is the one who decides how you want the output here to look like. Here they want to finish detecting all the 4, then only show you at E4 there. All right, at E4. Previously, continuously 4 times 1 already. Only at E4, when I is still a 1, then I output you a 1. All right, so of course, okay, with this one here, I is a 1, okay, I go output a 1, okay, because they already finish, okay, recognizing this one. Even though, okay, if they go back to 0, see, next state, even though they go back to 0, not this one, but they already show you that output is a 1 because you successfully detecting 4 consecutive 1. Okay, so I finished describing all the states already. Then, because, okay, I may, okay, creating some errors, or when I'm doing, okay, this part at the time, I wanted to know whether any errors will happen or not. So under here, you can add in when others. Okay, this is user defined, will not be compiled. So if they don't fall into this E0 up to the E4, then they will fall into this category called when others. Then you assert, remember this? Assert a logic 1, say that, oh, illegal state. Then you know that you have a problems in your these states here. Compiler will not compile this. Okay, it's mainly for user to sort of, okay, keep track of their own programs. And we are doing, okay, case statement. We need to end the case. We need to end the if. We need to end the process. So these programs here describe these state diagrams. And remember, okay, in these programs here, I run all these things here actually through the current state. Clock is not here, okay, through the current state. Okay, then how this whole thing, okay, can be synchronized? I need another process. Okay, another process here containing the so-called clock as well as the control signal. Okay, process here depends on the clock begin, clock 0 and not clock stable, means that they are talking about this one. Okay, your clock, this is a clock, they're talking about these conditions. Okay, clock equals to 0, go to 0 and stable signal, because you need to do a few things. See? So doing this a few things here require a little bit of time. So the states this event here, okay, may not be sufficient, okay, to do all this transition. So you see this, but it's when you go into the falling edge that time, when these things happen, they must make sure that this is at logic 0. Okay, then they do the changes. So next state will go into your current state. Of course, your current state here now is changing, isn't it? Okay. So I if and process this one. My current state is changing. So when my current state is changing, they will come back to here. Okay. Current state changing already. There is a change in this process sensitivity list. Then they repeat all this again. Okay. So when my clock here change again, it caused the current state to change for another one time. Then they will jump back to the top process. Okay, to repeat. Okay, do the checking of the I input conditions. So this is the way how you write your VHDL code based on state diagram. And we can see this, okay, in terms of our waveform. Okay, this is a waveform. Let's say my clock is this one, orange color. My input, take it as always 1. My output, this one here, let the program run. No? All right. So I started off, okay, at this current state EO. Because my I is a 1. So the next state, blur, you don't see it. You find out, okay, next state, I assign the system, okay, to take the next state as E1. Because my I is a 1. Okay, the next state will now become with the next state after these conditions here becomes the current state. Then check my I again, okay, during the next conditions of your clock. If I is a 1, then my next state I'm supposed to go will be E2. So E2 will appear at the current state. So because they need to do a little bit of processing, so you find that, okay, this is a part that they need a little bit of time to do the processing of checking as well as, okay, assign the 0 outputs. So at this instance here, I haven't detected 4 ones. My output 0. Proceed. The next state will go to E3 if my I is a 1. Proceed. My next state will go to E4. Actually, the moment you go to E4, very fast, okay? Your output here change to 1. Because when you reach E4, if you can reach E4, that is to say that the fourth input is a 1. Okay? So at the output of my signal here, I saw a 1 appear. Okay? So this is how, okay, I'm going to see for my these programs here, their simulation waveform. Of course, this part here, we have to imagine. All right, I only see these 3. Okay, so here got a little bit of questions here. What happens if a glitch occur on the output I? So let's say instead of constant 1 here, you see glitches. Glitches means a short durations of pulse. So in this case here, of course, it's a 0 lah, because you want it to be stable at 1, but somehow, okay, at some instance, they change it to 0. And glitches means that, okay, glitch means that short duration. So what is going to happen? Will it affect our outputs here? Okay, remember, okay, the signal must have the duration must be large enough, okay, for the systems to react. So if these glitches here is too short, okay, too short for my whatever gate that I'm talking about, they have this delay features, they have a transport features, the inertial timing. All right, if this timing here is shorter than the initial timing, sorry, they won't detect this. So no problems. Okay, no problems. But of course, okay, teachers keep on coming, then it then become very kacau. Okay, they say that your input here, well, please do something. But when only a single glitch, no problems. All right, no problems. All right, so this is on this parts here. And here I trace from this Google. So in Vhdl, okay, you may see things like this. All right. So this is logic 1, logic 0, high impedance. W, L, weak signal, weak 0, okay, pull down. And of course, these one are the common that we see. Don't care. Uninitialized if it's the new one. Okay. You haven't initialized, up to you. And no multiple driver. So not so common this one. So common one is this. Okay, 5. If you do simulations, things come out okay for all this. So at least you know what does it means. Okay. Okay. Now here say most of the time you will use 1 and 0 to indicate logic high or low value, and U will be used for representing uninitialized value, especially those RAM. Okay, programmable RAM lah. Okay, occasionally you will see X value. So this is indicating okay that you have some driver conflicts. The assignment here not so proper. All right, so that ends our topics on VHDL here. Any questions? Any questions? Okay, if no question, now this is VHDL, and I ask you all to do homework. Any one of you try this homework on this is VHDL tutorial. Yeah. Now we have done 2. The other day, Brian, okay, who answered this. Very nice diagram. Okay. Now I wanted to sort of okay write program for this one. need to do this, okay? Otherwise, your assignment, you don't know how to start. Now, any idea, okay, how we are going to do this? Part A, okay, divided into part A and part B. Now, part A is talking about these T flip-flops. Okay, part B, I combine, okay, 3 of these T flip-flops here to form a simple counter. And this counter here is asynchronous. Why I say asynchronous? Look at the clock. Okay, this clock connect to the main, okay, main input clock. This one, the clock input come from the previous output. Same thing, come from the previous output. So the clock is not connected together. So we call it as asynchronous counter. And actually it will show some ripple at the output. So they call it as a ripple, okay? Ripple counter, okay? Ripple counter. Okay, before we can write this, now I want to generate a flip-flop here called T flip-flop. Okay, T flip-flop. Any idea, okay, how T flip-flop work? I know I haven't covered, okay, this part, but from what you have learned in your year 1, okay, you know that T flip-flop stands for toggle. I didn't really answer. Toggle. So, do I know the truth table of this T flip-flops or not? I need to know the truth table, then only I can write the programs. So we do a little bit of groundwork first. So my input is T, my output is ground. Q here, okay? If I go according to this, it's QN. Okay, of course, okay, I must have a clock lah. Okay, so sometimes we just leave out the clock. We assume that the clock is working. Okay, the clock is continuously working, then only I can get this. I have only single input, okay, single input. Then now, since it's single input, 0, 1. My question now is, what is my output? Anyone can answer me? What is the output for this one? Adin, you mean here 1, 0? You mean 1, 0? Okay, any other different answer? Any other different answer? Okay, Zian say 0, 1. Okay, I need different answer again. 0, 0. Okay, one more answer. 1, 1. Wow. Which one is correct one? All the 4 possibility are all shown here already. Okay, which one is the correct one? Or anyone want to propose a different answer? Oh, don't care, don't care. Then what is the point of doing this? Okay, anyone want to propose a different answer? Actually, all these answers are wrong. That's why I keep on asking. Okay, anyone want to propose a different answer? All these answers are wrong. You got 0011. Wow, Zian, I cannot understand your answer. All these are wrong, okay, anyway. So I mean, is looking at this way, this way, T when 0, you say that, okay, output is a 1. T when 1 as an input, you say that output is a 0. Actually, all these answers are wrong. This is a T flip-flop, toggle flip-flop. Okay, I did this one when you are in year 1. Yes, you must always ask yourself, should I toggle? Should I not toggle? What does it mean by toggle in this case? Okay, what does it mean by toggle? Can anyone help me? Toggle means that next state change, okay? No change, okay? So T toggle, toggle, you can try to understand it as change, okay? Change, Okay, so when t equals to 0 is no change. Okay, no change. T equals to 1, then you say change. So in this case here, we have to analyze, okay, our t here. Should I change here? This is only input say no change. This is only input say that output change. Okay, so what should I put for my output? All these are wrong. Okay, so what should I put for my output? Yes, Q and Q bar. So if Q just now is Q, now T is a 0, so no change, remain as Q. If now T become 1, then you say you want to change, isn't it? How to change? Add a bar to it. Okay? Add a bar to it. Okay, so here got change. T equals to 1, you change. T equals to 0, no change. Okay? If the output you put it as Qn, you can just put this one here as Qn. Okay? Or Q. Okay, so this is how my T flip-flop here work. So I need to describe how it works under the architecture. Okay, I need to describe it. So any idea now how to write program for this one first? So after writing the program for this one, I need to make use of this one as component, and I build up this diagram. Okay, or these are schematic circuits. All right, I repeat, build this one, okay, as one component entity lah. Then make use of structural model, build up this schematic circuits. Okay, can I leave this homework for you all to think about it, other than I just give you all the answer? All right, so Monday, I want to see this. At least you all try first, think about it. Okay, so suggestion here is must use a signal. Okay, must have a signal, because this output cannot appear on the right hand side. So use signal to solve this problem. Right? Then we will build up this part. Okay, that is the question 1. Okay, question 2. Again, is a T flip-flops. Okay, now if this T flip-flops here got Q and Q bar, you can generate 2 output. But I look at this block diagrams here, you find that, okay, the Q bar never used. So if you don't generate this Q bar, it's okay. Then you're going to find that the program for this one here is exactly the same as this. Both clock this C is the clock here, are H trigger. Both are H trigger because you see the triangle. Okay, so you must use the event rising H. And for second questions here, this AND gate here, you don't need to generate. You can use this one here. Let's say this one here is a Q0. This is a Q0. This one here is the count enable. Count enable. So let's say I use a CNT. Okay, I just use a CNT. Then you can straight away just take, okay, Q0 and with CNT. Okay, just like this. All right, for this input here. And for this block diagrams here, you may need to use quite a number of signal. Okay, this one, signal. Okay, signal, signal, because you need to join the output to here. This one also, okay, signal, signal, signal. All right, because you need to bring it back to here. Bring it back to here. So you need to describe this connection. But these 3, once you describe these connections already, then you can just do it this way. Okay? And for this particular entity here, 1 input, 2 input, this is 1, 2, 3, 4 outputs. Okay? These 4 are output, and you can declare it as, okay, either vector or single wire, single bit, okay, either is signal, vector or single bit. But because this one here is a counter. Preferred answer is declare it as vector, because I need to see all these 4 output, then only I can tell you what is the count now. Just looking at one alone, no meaning at all. So I need to see all the 4. Then I tell you, okay, now it's count 5, for example. Things like that. Okay? I let you all try first. Okay? Rather than I supply all. So give you the hint how to start. Okay, so this one, just write, okay, the first one. If can already, straight away, you proceed with this. Then can continue with question tutorial 4. This part here actually similar to the segment that we do this morning. All right, but without clock. Okay, just write this one alone. So when ABC equals to this, you assign your output with these combinations. Okay, when ABC equals to another combination, then this is the output. Exactly the same as a segment, but without the clock, because a pure combinational circuit for this case here. All right, just for testing, that's why I only stop at 8. So train you all to be able to write this. Then question 2, D flip-flops. After D flip-flop, form all this. And form this circuit here. This circuit here, one input only, that is the clock, CLK, 3 outputs. And since this one here, state machines are usually the state machine, we will prefer this one to be in vector, because I need to see the 3 output at the same time, although it is not a counter. But I still want to see all the 3 outputs here at the same time. But before I can do all this, I need to generate, okay, a D flip-flop first. Okay, then call it out as component. Okay, now since I need to write this one, I must understand how D flip-flop work, the characteristic of D flip-flop. Anyone? D flip-flop is easier. Only one input, so again I put 0, 1, and over here, of course, my clock is always working. I assume my clock is always working. So what is the output for my Q? So this is more straightforward. Anyone can answer me? What is the Q output? Q output is a 0, okay? This one? Oh, 0, 1, yes, thank you. So actually, D flip-flop very easy, okay? You find that your Q actually same as D. Okay? In terms of this Vhdl writing, my Q output, okay, is exactly the same as D. What is the D value? Okay, this one, but of course you have to synchronize it by the clock. So try to learn how to write these programs here. And this is the thing that we are going to discuss next week. Okay, so I got some more. Okay, so at least, okay, we can do up to here first. Otherwise, okay, you write program, you have a little bit of problems. I don't know how to start. So next Monday, we have 3 hours, right? Yeah, we have tutorial. So we will spend 2 hours for our tutorial. Okay, 2 hours for tutorial and 1 hour, okay, for lecture if you can. Okay. I stopped recording already. So today we are going to end here with a lot of homework for you to do. And meanwhile, try to complete your lab, okay, the lab manual, follow. And next week we see the conditions. By right, we are supposed to go back. Okay, any question before I end today's lecture here? So try out, okay. I have all the answer for all these, okay, but I just find that it is not proper to let you all have all. So let you all try first, and Let me see, okay, where is your mistake? You all share out in the OneNote lah. Then now, if you're ready, okay, you just upload, okay? I see your mistake, then only I can tell you where you make your mistake and you alert, okay, with your own mistake. Now in the exam, okay, there's one question on VHDL. Question number 1. All right, write VHDL. It's not draw VHDL, draw block diagram. It's write the code. So you have to learn to write the code. Okay, any question? If not, I'm going to stop here. Okay, I didn't already say thank you. Okay, so in this case here, thanks for your attention. Wake you up so early in the morning. Okay, so I see you all again on Monday. So Monday is online. Okay, Monday online. Lecture tutorial, we do it online. Safer. So I see you all 9 o'clock. Yep, 9 o'clock. Okay, Monday. Okay, bye bye and see you all.